Okay, welcome to lecture. We'll get started in just a second. We're going to continue on from where we left off last time, which I think is right in this area. We're talking about sort of stoichiometry and yields. And again, we'll get started in just a second or so. As usual, if you do have questions, feel free to type them into the box there, and I definitely will answer your questions. Even if we happen to be past that area, we'll go back and make sure we get your answer. All right, so why don't we get started? We were talking about stoichiometry, and again, I think this is where we left off. And we were talking about sort of basic stoichiometry problems where you can basically do the mole-to-mole relationship. And there's really sort of four basic steps in a basic stoichiometry problem. Remember, you want a balanced equation. None of this works if you don't have a balanced equation. You need to convert what they give you to moles. A lot of times you'll be given things in grams, so you have to convert it to moles using the molar mass. Step 3 is usually the stoichiometry part, where you go to the balanced equation and find the mole-to-mole relationship. And that's usually between the two things you're interested in. Usually one thing you're interested in is what you converted to moles in step number 2. And the last thing you're interested in is usually what you're trying to find in the sort of reaction. And lastly, in the basic stoichiometry step, you will always be in moles after step number 3. Sometimes you will need to convert those moles into other units. And very commonly as well, converting those guys into grams from moles is a very common conversion that you have to do at the end. And that's basically the same 4 steps for any type of sort of stoichiometry type problem, a basic sort of stoichiometry problem. And a basic stoichiometry problem really is one where you're given just the starting amounts of just one thing in the equation. So maybe a reactant, maybe a product, and you could follow those same 4 steps to sort of solve that problem. A more complicated stoichiometry problem, which we also talked about as well, is a limiting reagent problem. And in a limiting reagent problem, that is typically a problem where you're given the starting amounts of both reactants. And that's usually how you can identify that it is a limiting reagent problem, is that you're given the starting amounts of both of those reactants. And when we talk about sort of the starting amounts of both of those reactants, what we're talking about is you're given enough information for both of those reactants to basically get to moles. So, and that could be grams of both of them, could be moles of both of them. Later on, it could be like liters of molarity. So, you know, if you have enough information to get to moles of each of the starting reactants, it is definitely a limiting reagent problem. And we talked about one way to solve these problems, which is through an ICE table. And you could use an ICE table to do that. ICE meaning initial, so that would be your initial moles. C meaning change, and E meaning end. And you can do basically an ICE table, and you can do a small little calculation during that ICE table to figure out which one's the limiting reagent. It's important to figure out the limiting reagent because the limiting reagent is always the one that determines how much product that you'll actually make. The other reagent in that case would be the excess reagent. So limiting reagent determines how much product it gets used up first in the reaction, and the limiting reagent, which is the one again that gets used up first, is always the one that determines the product or how much product did you produce. The excess reagent is something that you have there in a plentiful supply. You'll even have a lot of that excess reagent left over when the reaction is done. Now, one benefit to sort of the ice table approach like we did last time is you can relatively quickly answer a lot of questions that are typically asked of you in a stoichiometry type problem. You can figure out, how much of the other reactant, the excess reagents left over very quickly. If there's more than one product, you can figure out how much of the other product you would produce as well, in sort of a very quick sort of fashion. You don't necessarily, like I talked about last time, have to do the problem in an ice table fashion. Two other common ways that we sort of touched upon is to do two separate calculations, starting with each of the reactants and figuring out how much product each one would produce. And that would be your limiting reagent, also your theoretical yield. Another approach is to figure out how many moles of the reactants you have to start with and do a little calculation to figure out if you need to use up all of one of the reagents, how much of the other one you would need, and see if you have enough. So again, there's multiple ways to sort of do limiting reagent problems. We ended with talking about yields. There's the theoretical yield, which is always the yield, basically how much products produced from the balanced equation and what you're starting with, so how much you calculate. And that comes from a starting amount and the balanced equation. The actual yield is pretty much what it sounds like. It's actually when you physically do the experiment, it's how much product you produce. In a textbook type problem, that number is usually given to you in the problem. Somewhere they will tell you, hey, you produce this much of this product, and that would be your actual yield. The theoretical yield is typically the one that you have to calculate from the equation, and that could be a basic stoichiometry problem, could be a limiting reagent stoichiometry problem, but some way you need to calculate that. The theoretical yield, as we talked about, is usually your maximum yield. So usually your actual yield is less than that. Ideally, if you get close to 100%, that's pretty good. If you get over 100%, I think like we talked about last time, the unhappy face there, that usually means that you probably did something wrong. And again, if you get a really small percent yield, like 2%, 5%, you obviously did something very, very wrong along the way. To calculate the percent yield, that is when we take the actual divided by the theoretical times 100. And again, we're talking about percent yield, which I was just talking about, I hope, is what we're talking about in terms of we would like the percent yield to be near 100, and obviously closer to 0, not so good. All right, any questions on that stuff before we continue? All right, so I think we have another problem, if I'm not mistaken, which is this one. I don't think we did this one. Correct me if I'm wrong, but I don't believe we did. So why don't you take a few minutes, 5 minutes or so, kind of work through this one, see what you come up with. And here we're looking for the theoretical yield of TI in grams. And we're also looking for the percent yield if we produce 5.42 times 10 to the 6 grams. The molar mass of TI is 4788, which you might need. 4788. And the periodic table is the molar mass. The molar mass for these guys are given. They're basically grams per mole here. All right, so why don't you take a few minutes here, start working through this, and then we will get back together here and we will talk about the answer that you get. And if you're just joining, we are working on this example, so take a few minutes here and work through it. Okay, so let's take a look here and see how we're doing. So it'd be good to have that equation there. So we just write it down real quick. So again, I'm going to show you this doing the ice table method. And again, if you don't want to do the ice table method, you know another way, you absolutely could still do it that way. So let's see what we got going on here. So we have our equation here, which is TiCl4 plus a couple of magnesiums go to, where are we at there, Ti plus 2MgCl2, and we are going to basically follow the similar steps. So we first want an equation that's balanced, which obviously it is. The next thing we want to do, like we talked about last time, is essentially convert what they gave us to moles. And in this particular case, looking back, they gave us the grams of the TiCl4. They also gave us the grams of the magnesium. So we know, first off, that's how we do know that this is a limiting reagent problem. And we do need to figure out the limiting reagent because we have enough information from the grams of each of those guys to get to moles. So that is really your key to know this limiting reagent problem is when you have enough information like we were talking about to figure out the moles of each of those guys. So that's the first thing that we want to do is, again, we want to figure out the moles of each of these. So we'll just do it right here for now. We had 2.46 times 10 to the 7 grams of TiCl4. They were nice enough to give us the molar mass in the problem, which looks like 189.7. And that's going to convert our TiCl4 into moles. Since this is a scientific notation, we want to make sure we are using our exponent button. And it looks like we end up with something like 1.3 times 10 to the 5 moles of TiCl4. We want to do the same thing here on the other one. So we were given 1.13 times 10 to the 7 grams of magnesium. Again, we want to divide by 24.31 grams per mole, which was also given to us. And if we do that, gets us 4.65 times 10 to the 5 moles of magnesium. So again, these are our starting amounts. Of each of these. So if we're going to do our ice table approach, and we'll see how we did there, TiCl4 plus our magnesium goes to our Ti plus our 2MgCl2. Initially, we would put our moles in for each of these, which is 1.3 times 10 to the 5 moles. This guy is 4.65 times 10 to the 5 moles. And again, we could assume 0 of each of these. A reminder that when we get to the change part, we're going to represent that with an X. We're going to assume that the reaction is going to the right. So this is going to be minus X. It's 1 because the coefficient here is 1. Coefficient here, though, is 2. So we're going to do minus 2X. Coefficient here is 1. We're going to do plus X on the product side because it should be increasing with time. Coefficient here is 2 plus 2x on the product side because it's increasing. When we use the coefficients, as we talked about last time, it's really important because that essentially will give you the correct mole to mole relationship and the stoichiometry. So you want to make sure that you do use those coefficients. If you don't use them, then again, you will have the wrong mole to mole relationship. What we're going to do is just bring everything down. So 1.3 times 10 to the 5th minus x 4.65 times 10 to the fifth minus 2x, x and 2x in this case. At this point, like we talked about last time, we're going to figure out the limiting reagent by setting each of these guys equal to 0. So 0 would equal 1.3 times 10 to the 5 minus x, which means x equals 1.3 times 10 to the 5. We'll also set this guy equal to 0, our two reactants. Bringing our 2x to the other side and solving for x, which essentially you could just divide it by 2 if you want. Gives us an x value of 2.32 times 10 to the 5. So these two little calculations that I just did here is going to allow us to determine which one's the limiting reagent. And as we talked about, the one that is the smaller number will be your limiting reagent. So this guy is the smaller number. That means that this guy is my limiting reagent. So my TiCl4 is my limiting reagent. By default, my magnesium in this case would be my excess. That means essentially you don't need this number. And this X value that we just got here, and again, sort of the benefit of doing this table would be all of these X values that we see in this table. And that allows us, as we talked about, not really asked for in this problem, but it does allow us to sort of quickly calculate everything that we would need. So for example, in this case, we know that the moles of Ti equal X. And since X equals 1.3 times 10 to the fifth moles, we now can find out our theoretical yield by taking the molar mass at Ti, which was that 47, what was that, 4788, I believe. That last page, right? 4788, yep. So it's 4788 grams per mole. And that would get us 6.22 to the 6 grams of Ti. This right here, again, when you calculate it from the equation, is our theoretical yield. Any questions so far on that calculation there? It did want us to calculate, not necessarily just the theoretical yield, but it did want us to calculate the percent yield. And a reminder that the percent yield is the actual divided by the theoretical times 100%. And our actual yield is given to us in the problem. It's this guy down here that we underlined. So it's 5.42 to the 6. So our percent yield, 5.42 times 10 to the 6 grams, divided by our theoretical, which we just calculated, times 100%. And we will get, I believe, what you put in the box there. Pretty close. 87.1%, give or take with some rounding. Any questions on any of those steps there? Okay. Now, again, the benefit of sort of the table is if you were also asked how much of the magnesium chloride that you produced, you could really quickly kind of put it back in and go, my magnesium chloride is 2 times X, which would be 2 times 1.3 times 10 to the fifth. And again, in pretty much matters of sort of seconds or so, you can very much quickly come up with those kind of answers, like 2.6 times 10 to the fifth moles. which again, if you then looked on the periodic table and found the molar mass of magnesium chloride, you can multiply it by 115.2 grams per mole. And that would get you something like 3 times 10 to the 7 grams of that guy would be produced. And again, if you want to know how much of your excess was left over, you could put that X value back into there and figure out how many moles of your excess reagents left over, and then obviously figure out the grams. So again, sometimes people feel the ice table is a little beneficial in that sense because you can very quickly sort of figure out everything that you might be asked. But again, you don't necessarily have to do it the ice table approach. If you have some other way that you learned and you like it that way, you again should get pretty much the same answer, maybe slightly off, like we had there 87.4, I think, in the box. Maybe a little bit off with some rounding and stuff like that, but it should be pretty close no matter which way you do it. Any questions on any of those steps, where any of the numbers came from, or anything like that? All right, I think we might have, this is the one we just did, so I'll scroll that across the screen in case later while you're trying to sleep watching this video again, you could see again, this is a different approach when I'm scrolling across the screen. So if you want sort of a different approach there, you can take a look at this and it would give you sort of a different way than the ice table if you want. All right, so I think we got another one here. So why don't you take a couple of minutes, see how you do on this one. Let me give you some numbers that you probably need. We got carbon, that's 12.01 on the periodic table. Oxygen is 16. Nitrogen is 14.01 grams per mole. That's everything you need. All right, so take a few minutes and then we'll talk about it. We're looking for our percent yield here if we produce 120 grams of our product. Okay, so let us take a look, see how we're doing. So again, when we look at this, we should be able to recognize that it's a limiting reagent problem because we were given 100 grams of this guy and 100 grams of this guy. So again, we have enough information for both of our reactants to get to moles, which means it is a limiting reagent problem. So the first thing we want to do is make sure we got a balanced equation, which we do. The next thing that we want to do really is convert these guys into moles. So in this case, let's do it here since I got some room. We have 100 grams of NH3 and we have 100 grams of CO2. We want to use the molar mass from the periodic table to do that conversion between those two. And nitrogen 1401 plus 3 oxygens at 1.008 each, which I guess would have been good to give you that number, will get you 1703 as our molar mass for our NH3. And our 4401 here for our CO2. So we're just going to convert each of these into moles. And if we do it for our NH3, we got 5.872, not rounding too much here, 5.872 moles of NH3. We also will have 2.272 moles of our CO2. So again, this is just converting grams into moles using our periodic table and the molar mass. The next thing we're going to do again is I'm going to do it through an ICE table here, and we'll take our equation that we had on the other screen, and we have 2NH3 plus our CO2 goes to our product. And again, initially here, we're going to put in the moles that we just calculated, and that's 5.872 for our NH3. That's the 2.272 for our CO2. That's going to be 0 and 0. Change part here, again, we want to make sure we take those coefficients into account. So that's going to be minus 2x, minus x, plus x, and plus x in this case. Again, with those coefficients, that is what allows us to do the mole-to-mole relationship. We're going to bring everybody down. That's going to give us 5.872 minus 2x. Give us 2.272 minus x, x, and x. Again, we're going to set both of our reactants equal to 0. And we're essentially going to divide that number by 2 when we solve for it. And we get an x value of 2.936. We're going to set this guy equal to 0, which will get us a x value of 2.272. Here again, we're looking for the smallest. So this is our smallest. And by default, what that means is that is going to be our limiting reagent to CO2. The excess reagent will be our NH3. So we do want to use this X number, which again is how many moles that we have. And since we're interested in our product, we could go basically right into there. And we know that the moles of our product here equals X, which would equal 2.272 moles of our product. We then would want the moles of our product converted into grams because our actual yield is in grams. So we will have to go back to the periodic table here and get the molar mass of this product. And again, that is 2 nitrogens at 1401 each. We got 4 hydrogens at 1.008 each. We got 12.01 and 16. Gives us 6006 from the periodic table. The moles are going to cancel, and we will end up with about 136.5 grams of our product. This, again, because it was calculated off of the table or off of the equation, is our theoretical yield. Any questions on that so far? As usual with these type of problems, especially percent yield problems, if we go back and look at our problem here, not that far back apparently. Let's go back here. There you go. And if we look at our problem, again, the actual yield is usually always given to you in the problem. So we can now calculate the percent yield by taking our actual divided by our theoretical times 100%. Actual from the problem's 120 grams. Theoretical, we just calculated at 136.5 grams. We're going to times it by 100. And I believe you will be 2 for 2 there. You've got about 87.91% in terms of our actual yield. In terms of significant figures, while we might not round to 88, would be everybody pretty much in this problem has 4 significant figures. So that's why we'd probably go to 4 significant figures here in terms of our answer. Any questions on any of those steps, why we did any of that? Do you have to really know how to do this? The answer to all that is yes, you do, right? Any questions? Okay, so these are a little bit more complicated sort of stoichiometry problems, again, involving limiting reagents. Whenever you have a limiting reagent, you always need to determine which one is the limiting reagent, because again, that is the one that will determine how much product that you would make. And again, if you like the ice table way, you could do it this way. If you rather do it a different way that you still know, that's all good as well. All right, I think we are done with these type of problems, if I'm not mistaken. Again, what I'll do is I will scroll through this. If you want to watch it later, this is again a different method to solve the same problem we did with the ice table. And again, if you like this method better, you could use this method as well. Just gotta give it a sec there to get up there. All right. Hopefully they ended up with the same answer, so that's good. Okay. All right, so what we're going to move on to talk about now is solutions, molarity, and then we're going to kind of tie it back together with titration type problems. So a couple of things about a solution. A solution really is made up of 2 parts. Excuse me. A solution is made up of what is known as the solute, and the solute is the smaller part of the solution. So that's usually the smaller part. And we usually take the solute and dissolve it a lot of times in the second part of a solution, which is a solvent. And that is usually the larger part of a solution. A lot of times water, for example, is our solvent. It doesn't always have to be water, but it's a very good solvent for a lot of things. So for example, if you made a sodium chloride solution, you would take some solid sodium chloride, which would be your solute. You would put it into water, which would be your solvent. And when those two get together, that sodium chloride is going to dissolve, and that will give you a solution of sodium chloride. And those are the guys that have the aqueous symbol next to it. So that aqueous symbol means a solution, usually means a water environment. It's usually dissolved in something like water. How do you know what the solute is of a solution? It's a very simple sort of way. The name of the solution is always the solute. So if you have a sodium chloride solution that has the aqueous next to it, sodium chloride would be it. If you have a calcium nitrate solution, calcium nitrate would be it. If you had a hydrochloric acid solution, hydrochloric acid would be the solute. So the solute is really just the name of the solution. It is typically the smaller part that's dissolved. Not all solutions necessarily have to be sort of liquid. They could have gas and solids. So here's some examples of things that we might not think of as solutions, but for example, soft drink we do. The major component of the soft drink, like a soda, is water. It has sugar and other things dissolved in there depending on what soft drink you're drinking. Air is also sometimes referred to as a solution since nitrogen is the major gas in air. Nitrogen would be the solvent, while we have oxygen, argon, and some other things floating around. And then solder here, lead is the major component, and tin would also be included in there. So, usually when we think about a solution, we think about things being aqueous, but technically speaking, you could classify those other things as a solution as well. When we talk about a solution and solution stoichiometry, usually when we talk about solutions, there's a common unit of concentration that we use, and that is molarity. And molarity is big M, as it shows here. And what that is moles of solute over liters of solution. So the molarity is moles per liter. You could kind of think of molarity like a formula. You can use it to solve for any of those three things. So if we rearrange it and we want to solve for liters, liters would be moles divided by the molarity, and that is a capital M. And if you want moles, it is liters times molarity. So molarity is a most important sort of unit of concentration. When you have something that is, say, 4.50 molar, which is how you would say it, sodium chloride, what that means is that you have 4.5 moles of sodium chloride per liter of solution. So you would say that you have 4.5 moles of sodium chloride per liter of solution. The number always stays with the moles part, and it's always per liter. And if you do calculations, I highly recommend you get rid of the big M and you convert it into moles per liter. The reason I recommend that is because people always, when they keep the big M, have no idea where the liters is. They're not sure if they should be multiplying, they should be dividing. They're not sure if the liters actually got canceled or not canceled. So it's a very good practice to convert the big M into basically moles per liter. You could actually use molarity like a conversion factor. So if you needed to multiply by the molarity, you could use it just like this. Or if you needed to divide by the molarity, you could put the liters on top and do like a dimensional analysis type of problem and put the moles on the bottom. So sometimes we'll use the molarity like a conversion factor. And this conversion right here is one that is used a lot, where we take the liters times the molarity to get moles. Now, obviously, if you're not given the top part in moles, a very common thing that you are given is grams. So again, the molar mass from the periodic table will allow you to go from grams to moles. And the other common conversion, a lot of times you're given the volume in milliliters. So remember that there are 1,000 milliliters in a liter. So that's another conversion that's used a lot with molarity. So I think we might have one here, maybe. So why don't you give this a try? What is the mass of Ki that's required to make 500 milliliters of a 2.8 molar solution? K is on the periodic table 3910. And I is 126.9. So once you take a minute or two and see what you come up with, we're looking for the mass of potassium iodide that's needed. Okay, so let's take a look. So again here, when we have the 2.8 molar Ki, we have 500 milliliters of it that we want to make, and we want to know how many grams of Ki. So remember that molarity is moles per liter. If you're not sure where to begin, you can see that you have the molarity given to you. You don't have the liters, but you do have the milliliters. So you could solve for moles. And again, moles would equal liters times molarity. I would, like I said, take that 2.8 and convert it into moles per liter of Ki so you can see both units. And we do need to convert our milliliters here into liters. So again, 500 milliliters, we're going to divide by 1,000. And that's going to give us 0.5 liters. So we could take our 0.5 liters, which is our volume. We could use our molarity like a conversion factor, just the way it is, 2.8 moles on top, liters on the bottom. The liters will cancel each other out, and that would get us 0.5 times 2.8 gives us 1.4 moles of Ki. That's close to what we want, but we do want grams. So we do need these two numbers here to get the molar mass. And if we just need to add them together, since we have one of each, and that gives us 166 grams per mole as the molar mass. And again, we'll use that molar mass as a conversion factor, 166 grams of Ki per mole. Moles are going to cancel, and we will end up with 232 grams of Ki in this case. Very good. Any questions on that? So essentially, if we were to make the solution, we would weigh out 232 grams of Ki. We would dissolve it in enough water to have a total volume of 500 milliliters. We give it a shaky, mixy. When it's all said and done, we should then have a solution that has a molarity of 2.8 molar. Any questions on the calculation there? All right. So again, this is one way that you could prepare a solution like that using a volumetric flask. And again, you would put your solid in, you would put some liquid in. You typically would not fill it up to the narrow part. You would leave it down here, give it a mix until most of that dissolves. And then again, you would fill it up to the line there and the meniscus to that line. In a volumetric glassware, we typically have just one line that represents the volume in that particular case. Why don't you try this one? What is the molarity of a solution that is made by dissolving 42.5 grams of calcium chloride in enough water to make 250 milliliter solution? All right, so why don't you take a moment and calculate the molarity of that? I will as well, since I just made it up. Let me give you some numbers that might be helpful. Calcium is 4008 grams per mole. And what we got there, chloride, Cl is 3545. All right, take a minute or two and calculate the molarity of this solution. All right, so let's see how we're doing. So we're looking for the molarity here, which again is our moles per liter. Now out of this, we actually already have kind of the liters part, although it's in milliliters, so we do have that number. We do need to convert to get the moles, but we could get that from the grams part. So we do have to do a couple of conversions here before we can get the molarity. So the first one would be obviously to take our milliliters. We're going to divide it by 1,000 to convert it into liters, or just move the decimal point 3 places to the left. Gives us 0.250 liters. We will need to go to the periodic table, obviously, if it wasn't given to us, and calculate the molar mass. And if you do go to the periodic table and add it all together, looks like you get 100 and, call it 111. Do a little bit of rounding there. 111 grams per mole of calcium chloride. And that would get us 42.5 divided by that. Gets us something like 0.38 382. Wow, 295 if I don't round. And now we pretty much have both parts that we need, the moles and the liters. So to solve for the molarity, we would put those in. Hopefully I won't have as hard a time writing it over here. Moles divided by my liters. Again, I didn't do too much rounding at this point. And if we divide it out, it looks like we do end up with something like 1.53 molar. You could leave it as big M, which is what that's supposed to be, make it a little bit bigger. Molarity there of calcium chloride, or you can leave it as 1.53 moles per liter of calcium chloride. So you could do it either way to get the molarity. Any questions on that there? All right. So another process that we do with solutions, obviously, is we sometimes need to do a dilution on solutions. And sometimes solutions come very concentrated, which has a very high molarity or big M sort of number. And that process of dilution is the process where we add basically more solvent to a solution. And by adding more solvent, what that does is essentially will dilute down the solution. And it will dilute the solution down because if you look at the molarity formula, it is moles of solute divided by liters of solution. So when we add more solvent, like water, what we're essentially doing is increasing the bottom number. And when we increase that bottom number, what happens to my molarity is it will go down. So the bottom number gets larger. The overall number goes down in a dilution process. The important thing to remember when you do a dilution is typically you're only adding solvent or water in a lot of cases. And the moles of solute before you do the dilution and the moles of solute after you do the dilution are always going to be the same. The only thing that you're changing is basically adding that more solvent. And there is a dilution equation, which is down there. And most people refer to it usually as M1V1 equals M2V2. And this is usually the dilution equation, which is basically what's on the bottom there. Our ones are usually before the dilution, the more concentrated. Our twos are after the dilution, more diluted part. Truthfully, it doesn't matter as long as you keep the molarity and the volumes together. So M is molarity and V is volume. M is molarity and V is volume. Now, when you use this equation, volume actually can be in milliliters. It's okay, as long as it's in milliliters on both sides. R, it could be in liters. You could do it either way. And M is obviously usually molarity. And the reason you can when you're using this equation and not when you're using volume and molarity by itself in a non-dilution equation is if you solve for V2, for example, that would be M1 V1 over M2. And if we just put those units in, that would be molarity, and we left it in milliliters, divided by molarity. Molarities cancel, and you end up in milliliters. Technically speaking, if you take milliliters and you times it by molarity, what you get is not moles, you get something known as millimoles. And then if you divide the millimoles by milliliters, the milli part of it cancels out and you're back to molarity. Yeah. So you technically, if you're using this dilution equation, can leave the volume in milliliters. It's perfectly fine. It just means that if you do solve for volume, you will get milliliters out. If you're more comfortable, you could convert it to liters and then times it by the molarity. And again, that means you'll just get liters out. So, but just to be very clear, if you're simply using volume times molarity, it should be in liters because that will give you moles by itself. If you did it in milliliters times molarity, again, that will get you millimoles and not moles. And you may be off by a factor of 1,000 if you don't catch that correctly. So make sure if you're doing sort of molarity and volume by itself, that you convert it to liters. If you're using this dilution equation here, M1V1 equals M2V2, you can leave it in milliliters. Any questions on that? You will also sometimes see this dilution equation written C1V1 equals C2V2, where C is just a generic unit of concentration. Most people will use the M1V1 equals M2V2 because molarity is the most common unit of concentration. But technically speaking, you could use that equation with other units like percent mass to mass, which we'll talk about. You could do percent mass to volume if you want. You could use some type of unit like percent volume to volume. You could use molality. So technically, it doesn't necessarily have to be molarity in this dilution equation. but probably 9 times out of 10 it will be, because again, that is the most common unit of concentration that we have. So why don't you calculate this? How would you prepare 60 milliliters of a 0.2 molar solution of nitric acid from a stock solution that is 4 molar? So take a minute or two and figure out how you would make that solution. All right, so let's take a look and sort of see this. So we're preparing a 60 milliliter solution that's 0.2 molar of nitric acid from a stock solution that's 4 molar nitric acid. Obviously, it's nitric acid, no type of reaction. We're just doing a dilution. So again, that should make you think of the dilution equation here. And visually, sort of what's going on, right, is we have a bottle over here that is 4 molar nitric acid, more concentrated. We then want to make another container that has a total volume of 60 milliliters and also would have a molarity of 0.2 molar, also going to be nitric acid. So we could do M1 V1 equals M2 V2. Usually the more concentrated one is the higher molarity. So this would be 4 molar. V1 in this case is what we're solving for. M2 would be our more dilute solution, which is the 0.2 molar, and we're making 60 milliliters. Here again, I can leave it in milliliters because when I solve for V1, which would equal 0.2 molar times 60 milliliters divided by 4 molar. The molarity here is going to cancel. So this is what I was talking about before. This will give us the answer in milliliters. If you want to convert it to liters, you can. You will get the same answer other than your answer will be in liters and not milliliters. So since I did not convert it, I'm going to get 3 milliliters as my answer. Now, the question actually asks how you would make this solution. So when we get that 3 milliliters, what that represents is 3 milliliters of the more concentrated solution. So typically when you solve for V1, that's how much of the more concentrated solution. So technically speaking, we would take out of this guy and put into our new one 3 milliliters of our nitric acid. The rest of it here would be water. And would I put, in this case, 100 milliliters of water on top of it? Not 100 milliliters, 60 milliliters of water, I'm sorry. Would I put another 60 milliliters of water in with it? And the answer would be I would not put 60 milliliters of water in it, because if I put 60 milliliters of water, plus the 3 milliliters of the nitric acid I already put in there, my total volume would be 63 milliliters. So what I would want to put in here is 57 milliliters of red water, apparently, of red water, right? So my 57 milliliters plus the 3 milliliters I already threw in there gives me my 60 milliliters of total volume that I want in there. Again, if I put 60 milliliters of water in there, we would have a larger volume, and actually the molarity would be smaller. And if I give this a good mixy mix, shaky, shaky, this solution then should have a molarity of 0.2 molar in this case. So usually a lot of times when you're doing a dilution problem, they oftentimes will ask how much water you need to add. And generically speaking, usually the volume of water or solvent is V2 minus V1. So usually that's one way that you can sort of calculate how much water that you need. As my V goes crazy there. Let's just try that again. There you go. Question on this dilution problem. Again, you want to make sure that you do read the question, because very, very common dilution problems, they do ask about the water. So like this, they may ask how much water you would put in there. They may say, hey, you started with 25 milliliters of the solution and you added 100 milliliters of water to it. So oftentimes people mess up on these dilution problems with the sort of the water component of it. Any question on dilutions? Okay. So what we're going to talk about now is sort of putting two things together. We're going to talk about putting together stoichiometry and also solutions. And solution stoichiometry really is sort of the same approach as a traditional stoichiometry problem. The main difference is you will oftentimes use liters times molarity to get to moles instead of grams to moles using the molar mass. So we do basic same steps. Could be a regular stoichiometry problem, could be a limiting reagent stoichiometry problem, but somewhere along the way, either at the beginning, we'll use liters of molarity to get to moles. We may use molarity and moles at the end of the calculation to get to volume. And we may use moles and volume to get to molarity at the end. So somewhere along the way, we're going to use sort of molarity and volume and moles somewhere in that problem. And again, it may happen at the beginning and the end of the stoichiometry problem. But the middle part of the stoichiometry problem is basically the same. Now, one type of method is what's known as gravimetric analysis. And this is where we mix two solutions like we see on the bottom there. We mix the two solutions and a solid is formed, that white precipitate. We then would typically filter this white precipitate through a filter paper and let the filter paper dry. And that would give us basically the mass of the solid that was formed. And again, you could predict how much solid you would form if you knew the molarity and the volume of just one of these guys. Actually, if you need, like, say, the liters and the molarity of this guy, you could do a stoichiometry problem, again converting to moles, doing the mole to mole relationship, and then doing moles to grams using the molar mass. And you can figure out your theoretical yield that you would get from the equation. This obviously would be if you physically did the experiment. This would be your actual yield. And you could divide the two and calculate something like percent yield like we were talking about in the earlier problem. So again, you could do sort of a basic stoichiometry problem. And again, the information you may be given may be liters and molarity, which would allow you to get the moles and do the stoichiometry part. Another common method that's used is one like the next big experiment that we're going to do, which is titrations. And titrations are also really solution stoichiometry problems. And in a titration, we typically will add a solution of known concentration to a solution of unknown concentration. And we usually will use a burette, which is this guy here. And a burette, again, is a long glass tube. It has a little opener and shutter, which is known as a stopcock, which will allow the solution to run in. And if you do sort of a acid-base titration, for example, you could have your acid on the bottom, and the top you could have your base, and then you pretty much would add your acid to your, your base to your acid in this case. And you would continue to add your base to your acid until you reach what is known as the equivalence point. And the equivalence point in an acid-base titration is when the moles of the acid will exactly equal the moles of the base. So exactly at the equivalence point, you have added enough base, in this case, moles of base, to use up all the moles of your acid, essentially. The equivalence point shouldn't be confused with what we sometimes refer to as the end point of a titration. The end point of a titration is pretty much when you stop your titration. And if you do a good titration, the end point where you stop and the equivalence point should be pretty close to each other. So you may ask yourself, how do I know when to stop the titration? And the way we know when to stop is that we use an indicator. So a very common indicator is phenolphthalein. And that's an acid-base indicator. And most indicators work over a pH range where they have different colors. So for example, phenolphthalein, we'll get the right color for this maybe, is pink. So around a pH of 8.3, phenolphthalein is actually colorless. And then as you head towards a pH of 10, you start to see a tinge of pink forming, tinge of pink, a little darker pink. And then as you get closer to that 10, you see this really pink color sort of occur. And something like phenolphthalein is actually colorless in acidic and acidic and neutral solutions. And it turns this pink color in basic solutions. And why phenolphthalein is used a lot is a lot of titrations that we do, especially the one we're supposed to do in the next experiment. A lot of those titrations, the equivalence point will be basic. So the equivalence point will be basic. And that makes phenolphthalein work really well for those type of titrations because you're able to see this pink color develop in the solution like we see over here. And that's sort of a visual indication to you that you should stop your titration. It's usually a visual indication that you have hit the equivalence point, and that will tell you, okay, I should stop at this moment. Now, in a titration like we would typically do when we take something like acetic acid, which is vinegar, with some sodium hydroxide. So in that example, our sodium hydroxide, which is our base, would be up here. Our acetic acid would be in the beaker. When we do that titration, the pH is around 8 point something at the equivalence point. And that's why typically when you use phenolphthalein in the titrations that you typically would do, they typically yell at you that you should try to get the lightest color of pink that you can see that stays. That color does need to persist and stay. And that is why, because the lightest color of pink, that it's so light that you essentially will have to put like a white piece of paper underneath it to kind of see the pink color. And the reason for that is that means that if you stopped your titration at that point, you would be back in this range in terms of pH, which is probably very close to the equivalence point, as opposed to if you titrate like me and just open it up and let it go. And you got this super dark pink, which would put you on this side of the indicator, like a pH of 10, you perhaps have jumped way past the equivalence point. You might not have, but you might have jumped way past the equivalence point and not get the right one. There are all kinds of different indicators, and for example, phenolphthalein would be a terrible indicator for a titration where the equivalence point would be acidic. So it's possible to have a equivalence point near an acidic pH. You could also have an equivalence point near a neutral pH, and you could have one that's near a basic pH. And there's a lot of different indicators that change color. For example, bromothymol blue, I think, something like that, is kind of like a yellow color and then goes to like a blue color in terms of that pH range. And it kind of changes color in more of the acidic range. So that would be a really good one to use for something where your equivalence point would be acidic. Phenolphthalein would be terrible to use in that case because it would not change color to indicate it would still be colorless in that acidic solution. So there's a lot of different choices. Phenolphthalein, again, is a common one that's used because usually in chemistry and classes like ours, in the classes that you take, they oftentimes will give you vinegar, which is acetic acid, and they'll give you sodium hydroxide, which is a strong base, and that will always yield a basic sort of pH around that equivalence point. But there's a lot of indicators that can be used. And what you oftentimes will see sometimes if you've done a titration before is sometimes you'll hear people say this very common phrase, I don't understand it. I just added 1 drop and it went from no color to like super pink. Just like really quick, it went from super pink. And I just added 1 drop. I thought I was near my equivalence point. I have to do the titration again. I mean pink like this. We'll make this guy nice and pink. And the reality is, if you are doing a titration really sort of properly, which is you're adding the sodium hydroxide or the base very slowly, for example, and you're doing it sort of drop by drop, the reality is if you sort of went from no color with 1 drop to dark pink color with just the adding 1 more drop, you're usually probably okay. And the reason why that happens is when you do a titration, and you'll learn more about this in 1B or 200B, whatever they call that, you can make a titration curve, and the titration curve looks something like this. And we'll call our equivalence point right about there. And what we see, pH is on the Y, and the amount of base in this case is on the X. And what we see is typically when you approach the equivalence point, it goes up sharply and vertically, right? And when we go sharp and vertical as we approach the equivalence point, what that means is our pH is changing a lot. Yes. So our pH here is changing a lot. But if we go down to our volume, which is on the X, our volume is not changing very much. And that is why you can do a titration. And as you approach the equivalence point, you typically will see a jump in the pH to the equivalence point. And then you'll see another jump in pH past the equivalence point. And what that sometimes will do is this part right here. When you add that 1 drop, although you're not adding a lot of volume, you potentially could be changing the pH a lot. And you could jump the equivalence point in terms of pH and move your solution to a higher pH, even though you didn't add a lot of sort of solution to it. And visually what you will see is it will go from colorless to this really dark pink color with just the addition of that 1 drop. And it's a very common thing people say, maybe you said it if you've titrated before, I don't get it. I just added 1 drop and it went like super pink on me. And that is again because you're not adding a lot of volume, but that little bit of volume is enough to make the pH change a lot. And by making the pH change a lot, it's enough to make that indicator's color change a lot as well. And that will obviously change the color. So like I said before, it's not really tragic if you are adding sort of the base from the burette sort of drop-wise. And if you miss it by a sort of a drop, you're still relatively close to the correct volume. It would be probably way off if you added, from the burette like I might do, where you just, open it up and just let it drop all in like a big stream of sodium hydroxide rather than doing more of a drop by drop or a very slow sort of drop from the burette. And in that case, you could definitely jump way past the equivalence point, both in color and in volume. But if you're very careful as you're adding it and you're going slow, even around the equivalence point, you can go very slow and you will probably be okay, even color-wise. You know, the color doesn't look super light pink. This one looks darker, the other one doesn't. So usually when you do a titration like what we would typically do in this next experiment, you know, more importantly than necessarily the color, you should try to get the color light pink, but more importantly is the amount of base that you would add. If the volume of base added for each trial is fairly consistent, usually you'll be okay in terms of the numbers and stuff like that. But if you have a wide variety of volumes to get to the equivalence point, so for example, the first trial took you 10 milliliters, second trial took you 22 milliliters, the last trial took you 15 milliliters, you know, your numbers are probably all over the place, not going to be very good. But if you like the first trial took you 15 to get to the equivalence point, next one was like 14.9, next one was like 15.1, you know, they're all within the same sort of ballpark, you know, you'll probably be okay. Questions on titrations, which is really the next big experiment that we will start technically probably on Thursday. Any questions on that? All right. So I just like to go through this example so we can kind of get through titration here, and then we'll call it a day here for lecturing. So this is a titration problem just to kind of show you how these work. And a titration problem is essentially a stoichiometry problem that involves basically molarity and volumes that I talked about before. So what we want to do in a problem like this is we want to make sure that we start with a balanced equation like normal. So we would take our sulfuric acid, which is an acid, and we would react it with our sodium hydroxide, which is a base. And again, in this case, we're probably adding sodium hydroxide up in the burette. And we have our sulfuric acid down in the beaker. Again, we're adding our sodium hydroxide to it. This is a double displacement reaction or an acid-base reaction, right? So we're going to make water, right, as one of the products. Water is going to come from the OH from the acid, from the base, and the H from the acid, and we'll make some sodium sulfate. Again, sodium is +1, sulfate is -2. You want to make sure you get the right formula when you do it. None of stoichiometry works if you don't balance the equation. So this equation is actually not balanced. So you want to make sure that you do balance it. And perhaps we need a 2 there, and perhaps we need a 2 there as well. That's going to balance it. Now, when we look at what is sort of given to us in this problem, we have, in terms of the sulfuric acid, we have 25 milliliters of the sulfuric acid, and it has a molarity of 4.5 molar. In terms of the sodium hydroxide, we have the molarity of it, and we're looking for the volume, right? So remember that molarity is moles per liter. So we obviously have the molarity for the sodium hydroxide. We do not have the moles, so we need to find it, but we are looking for the volume, right? So the moles of the sodium hydroxide is going to come from the stoichiometry part. And we could do stoichiometry here because with these two pieces of information, we have enough information to solve for moles. And that's basically what we want to do. So again, instead of using grams in the periodic table to convert the grams into moles, we're going to use the volume and molarity and solve for moles, which is liters times molarity. So starting with our H2SO4, we do need to convert our milliliters into liters. So we want to divide it by 1,000. We are going to use our molarity and convert it into moles per liter. And in this case, 4.5 moles per liter of our H2SO4. So this part here is very much like what we do in a stoichiometry problem when we take the grams that's given to us and the molar mass and convert it into moles, except here we're using liters and molarity. That gives us 0.1148 moles of H2SO4. That is close to what we need, but we're still at H2SO4. Remember that we're looking for sodium hydroxide. So we do need to do some stoichiometry, and this is why, again, it's important to have the balanced equation. We see that for every 1 mole of H2SO4, we get 2 moles of sodium hydroxide. And just like a normal stoichiometry problem, we're going to use the mole-to-mole relationship to get rid of the moles of H2SO4 and replace it with moles of sodium hydroxide. The moles of the H2SO4 will cancel, and that will get us 0.2295 of sodium hydroxide. So hopefully you can kind of see here the steps are kind of the same as a normal stoichiometry problem. And that essentially is the thing that we needed for our sodium hydroxide. So what we could do now is use the molarity that's given to us for the sodium hydroxide, which is 1.420 moles per liter sodium hydroxide. And we could use the moles that we just calculated and take our 0.2295 moles of sodium hydroxide. We are going to divide by the molarity. So we're going to put the moles on the bottom. And again, I would use both units so you can see it. The moles are going to cancel. And we will end up with 0.162 liters of sodium hydroxide. Or if you wanted in milliliters, 162 milliliters of sodium hydroxide would be needed in this case. Now, this is a basic titration problem. And again, as I mentioned, usually titration problems are stoichiometry problems. So if you remember our 4 steps, balance the equation, convert to moles, except here that we're using liters and molarity to do that. Use the mole-to-mole relationship from the equation, just like a regular stoichiometry problem. And lastly, convert our moles into some other unit. And in this case, we're converting to liters. So this is a very common sort of titration problem. And occasionally at the end, you may have to convert into molarity, which is moles per liter. And if you did in that case, you would be given the volume. Yeah. So a variation of this problem would ask you to find the molarity, and you would need to divide it by the liters as given to you after you find the moles to figure out the molarity. Any questions on any of those steps there? So again, really important to make sure that you do have the balanced equation. And thank you for that correction there. I think I did write that backwards, huh? Sorry. This corrected here is 125. Thank you. Getting old, I can't see. So let's just correct all that across. So that is 2. So that would be 0.225 moles. Thank you. And lastly here, I guess it helps to look at the calculator correctly, huh? 1.420 So about 158, thank you. 0.158 liters. Sorry about that. 158 milliliters of sodium hydroxide. Thank you very much for letting me know. I'll do the classic, just making sure you're listening out there. Nah, I just screwed up. There we go. All right. Thank you very much. So it should be, again, the correct answer here should be 158 milliliters or 0.158. Again, make sure you look at the calculator correctly and stuff like that. Any questions on the steps here for a titration problem? And like I said, sometimes the variation on it is at the end you would be solving for molarity. Okay, a couple of things here. We'll stop lecturing there. We're pretty much almost done with this chapter, I believe. So we got a few more things to talk about in terms of solutions and concentrations. We did get through here titrations, which should allow us to probably begin the titration experiment. We're going to begin it next Thursday. So I'll put it up there and everything. You'll be able to start it next Thursday. And we'll talk more about that on Thursday. It's a sort of a big experiment. It's a formal experiment. So we'll talk about what you'll need to do. And I'll put up the links, obviously, on Thursday for the videos for experiment 10, I believe. A couple of reminders, I believe experiment 9 and study assignment F is due on the 30th. So that's due on the Thursday coming up. So those again are, I believe, redox type of stuff. Study assignment G, which technically I said I think you could have started most of it last time. You should now be able to complete the rest of it after this sort of example and what we talked about today. So study assignment G will be due, I believe I made it next week. So that's coming up to submit that, which I believe is stoichiometry. And again, officially we'll start experiment 10 on Thursday, this coming Thursday. I'll take a break now. So maybe around 7:30. If you have questions, you could come to the lab and I'll be happy to answer any questions. Again, still out there, what you should have is experiment 9, study assignment F, and I believe study assignment G as well. And again, if you have any questions on any of that stuff or the stuff we've been talking about here, I'll be more than happy to answer your questions and all that stuff starting at 7:30. Yes, sir. What's your question? Okay, I'll double check. I haven't had a chance. I've been teaching all day. I'll double check and I'll get back to you based on what you sent me. Okay. In terms of the exam and all that, it should have been graded. You should be able to see it. You should be able to look and see what was sort of marked wrong and that type of stuff. So that should be up there as well. And I'll try to do a grade update shortly. I'm not sure the grade book because everything's kind of weird if it's all exactly correct or not, but I'll double check everything that's in the grade book. All right, so I'm taking maybe a 20-minute break. So about 7:30-ish, 7:35. I'll open up the lab one if you have questions. If not, I'll see you Thursday. And I continue to work on study assignment G, which you should now be able to complete, and the rest of the ones as well. All right, so we're going to end this one right now, and about 20 minutes or so, I'll open up that lab one for any questions.